recording. Okay. Hi everyone. Welcome to Learning Quantum Core for Application. This is session 6, the last of the...
Prakash, I cannot hear you.
Oh, you cannot hear me? Oh, okay. Maybe because of the recording. No, recording is there. How come I'm not being heard? Let me try if I have to change the audio. Oh, okay. I can do one thing. I will join from the cell. Yeah, just a second. I can do that. Give me a second. I'm going to join from the learning quantum, right? Let me join from, there'll be, hi everyone. Welcome to Learning Quantum Core for Application Session 6. I hope everybody is hearing. Gokhale, can you hear me now? Are you able to hear me, please? Somebody
Yes.
respond. Very good. Thank you very much. So what we are going to cover today is Learning Quantum course for application. This is session 6. This is co-sponsored by QML Meetup Group as well as Emerging Open Tech Foundation, EOTF. So we had covered session 1 to 5, starting with overview of quantum, math and science behind, and then we went into some exercises, did something on the gates and the logic and something on the algorithm. And the overall picture, as you see, includes the various topics like the qubits, the computing portion of it with the infrastructure underneath, the communications which relates to the channels, the classical as well as the quantum channels, and then the left side, the sensing, which includes the PNT, that is the positioning, navigational, and the timings, and the top one, which is algorithms, which includes the gate optimization. We are not covering adiabatic quantum, as you know, so this is mostly related to what you call gate-based quantum gates. So today's we'll cover the base once again, because this is concluding session. We want to make sure that we cover the basics of quantum, the QFT, shores, sensors and application, extension, exercises, and conclusion. So it's 10 past 10, almost 10 minutes. So let me start with the presentation on the basics. So you remember when we covered the basics, we talked about the circuits, and in logical circuits, normally, that is in the Boolean logic, in the digital computing, opposed to quantum computing, we use bits, and we have sequential circuits. So we have example here, a NOT gate, AND gate, this is OR gate, and then combining together with the NOR, using the NOT and the ORs, and then this is a circuit. Now this has a multiple input, it may have only one output. Compared to that, if you look at the quantum circuit, it will have n inputs, n outputs. So basically it is also similar to this, but the differences are that in quantum circuit, it's reversible. So what you give here, you can bring from the other side, it should work the same thing. So it is reversible in one sense. At the same time, it is discrete time based. So you have got the qubits, which are, this is going MSB, that is, this is LSB to MSB. So the MS bit is here. So this is MS bit, and you are applying the various quantum gate logic here. And so there is a difference. Obviously, there is no clock here, whereas in this case, this is usually sequential, combinatorial, as well as you can do it on the basis of clock. Here, it's not clock, but it is discrete time. Now, that discrete time can be anything. It doesn't require any specific, but you do one at a time, one shot at a time, and that is how it is. So there is no synchronized mechanism in the QPUs, whereas there is a synchronized mechanism in the CPU. So that is why we talk about no clock, discrete time in the quantum. And the other point is that this is based on abstract model of states. Like here we talk about the digital numbers, binary. Here you talk about the abstract states. And the states are nothing but either or. That means if you have one qubit, it has two states, which is the spin up and spin down, or ket 0 and ket 1 respectively. And so you tend to ensure that when you measure, they will collapse to one or the other. But normally they will be superpositioned. That means 0 and 1s will be there, and it can be 1 qubit, it can be 2 qubit. This is a 3 qubit circuit. So you have 3 qubits, so 3 qubit input, 3 qubit output. That means 2 to the power 3, 8. That means 8 states are the, one of the 8 states it will fall to, depending on what your inputs are. So this is a representation. Here is a block sphere representation, which represents the qubit in the XYZ three-dimensional representation of a two-dimension. So basically, when we say qubit, it is Hilbert space, which is virtual. It's a vector. So if we call a vector, it's represented as ket psi. So ket psi is a combination of alpha ket 0 plus beta ket 1. Alpha and beta being the probability density functions values, that is a magnitude. Alpha square plus beta square equal to 1. And then this is alpha and beta can be imaginary. So they can be in the real axis as well as imaginary axis. So they themselves will have two variables, A plus IB, C plus ID types. So that means I is the imaginary, or the you can use in Python J or I, whatever you use. But that means what, 4 variables are there, and they cannot be represented in real flat 2 dimension. So there is a way to represent that in 3 dimension using the axis X, Y, and Z, and therefore we call that as a block sphere is a unit sphere with X, Y, and Z direction. X. So the standard basis of measurement. So when you measure, they collapse. So which qubit it will collapse to? This one, this one, this one. Each one of them will collapse to one of the states. So 2 to the power 3, 8. Out of the 8 state, it has to collapse to one state. So what state will that be? 0, 0, 0 or 1, 1, 1 or anywhere in between? So that question is answered by the Q sphere, block sphere, and the block sphere is only for 1 qubit. It is a 1 qubit representation for 3 dimension. We generally cannot have for n dimension, but for the purpose of whatever qubit it collapses to, we can figure out, and that is what we are going to do. So the directions x plus x minus is one direction, y plus y minus another, z plus z minus. So z basis is the standard basis. So your ket 0 is spin up, ket 1 is spin down. So we are always going z basis as the standard basis. The second basis called x basis. It can be plus or minus, and that is called Hadamard basis. You can also have y basis, but generally not used because x and y is a surface plane. Therefore, we don't really use it. It's either standard basis, ket 0, ket 1, or Hadamard, which is plus minus basis. So it's called as ket plus and ket minus, with a plus and greater than symbol as we used. So programmatically, you can control the quantum effects through superposition, and that is for the usually for the parallel computing. And then entanglement, loosely we can call it as it is when the qubit is rotated with some condition, then that it gets entangled. So that's the picture of entanglement to in a simple terms. There is a pure state, there is a mixed state. Pure state means either it is in 0 or 1. But if it is in 0 and 1, and if you have more than every operation in quantum is a tensor operation. And the tensor operation is if I have A, B, C, D as a matrix 2 by 2 and E, F, G, H, then every element of the first 2 by 2 matrix is multiplied to every element of second, and then whatever the resulting 4 by 4 matrix comes, that is the tensor product. And that tensor product can be applied anywhere. It is everywhere. So therefore, if I say ket psi, ket phi are 2 qubits, then the product of the ket psi and ket phi will be psi phi as a ket together, combined together. So that is a tensor operation. That tensor operation may result in 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0, and 0, 1, 1, 1, 1. So 4 states. So, but the collapse will always be to one of the states, and that is what is represented here on the standard basis. So usually the presentation is always on the standard basis. So let me move on to next. And just to ensure, yeah, there is Suresh Sharma. Suresh, welcome. So we'll now go to the next slide. Here I am showing you a quantum circuit, quantum computing circuit. The model is like this. Usually we call I identity, that is diagonal matrix 2 by 2. If I say then 1, 0, 0, 1. So this is diagonal. 1, 1 is diagonal. Whereas if I say 0, 1, 1, 0, that is off diagonal. Off diagonal is usually X. Whereas diagonal is always, if it is diagonally 1, that is identity or null matrix, you can call it. So if you multiply I by I, it will always be 1. And that can be, this is not multiplication, this is tensor multiplication. So when you tensor multiply I with U4, it will result in U4. So if you look from this point of view, here is U4. What we are saying is that this is from reverse. So because you have to start from here, so we should look at this way. So if you have 4 qubits, these are 1, 2, 3, 4, every line represents a qubit. If you give an input here 0, 0, 0, 0, then whatever that is, it can be anything, 1, 0, 0, 1, whatever input you give, it flows in time like this. So when you flows in time, then you go to identity matrix. So wherever there is nothing, null can be applied. So there is nothing here, you can apply a null. Here is nothing, can apply a null. So I, U1. So basically I into U1 into I. We start with MS bit. So I into U1 into I, that is 1. Then the second vector is U3 into I into U2. U3 into I into U2. The third one is U4 into I into I. U4 into I into I. So that's the way the circuits are designed and modeled. So the circuit model is the representation of the unity. This is called unitary matrix, and I is the null matrix. Because the product is always going to be 1, because you are in the unitary circle, as I described to you earlier, we are always on unitary circle, the result. So any transformation is nothing. Given a vector in any of the space on the sphere, it is just being rotated either clockwise, anti-clockwise, depending on the phase. And the phase is what? Local phase and global phase. Global phase is meaningless because it is just a mathematical representation. But local phases do have their so even there, the local phases you can have in the what you call the terms of theta and phi, or it can be any of the negative positives based on the eigenvalues and all that. So I'll just move on to the next one. Here is one example of a quantum gate. And so we are talking about 3 poly gates which are important: poly X, poly Y, poly Z. So when you say poly X, as I said, it is off diagonal 1. Identity matrix have diagonal ones. This is 2 by 2. So basically 2 by 2 means it is a, we are talking of qubits, 2 qubit gates will have 2 by 2. So 2 by 2 for single for a single qubit you will have 2 by 2 matrix. For 2 qubits you will have 4 by 4. For 3 qubits you will have 8 by 8. So this is 2 by 2 for a single qubit. A single qubit here is a matrix. This is poly X, this is poly Y, poly Z. And the way to remember, high for a X, it is off diagonal 1. for a y, it is what we call as, in this case, you multiply by I because you are talking about the imaginary axis plus I for the y, and for the z, which is the standard basis, which is what we go with the top and the bottom being the spin up and spin down. And so 1 0, so kit 0 is represented by 1 0 column matrix, and kit 1 is represented by 0 minus 1. So this is the z matrix, the standard basis measurement. So we can talk about the poly X, and you can always see the trace of all polymetrics is 0, and energy levels, that means they don't have any energy. Energies have to be when you multiply, when you do something, then only you can evaluate. Usually the trace of a matrix is the sum of the diagonal divided by the normalization factor of square of each of these items. So for polymetrises, the trace is 0. That means their energy is 0. But they are operators. When they operate on any of the gates, they change the state, and that is why it is important. So one is, this is equivalent of a quantum gate, which is a NOT, and then you have Y. So this representation goes like this: X is also represented as sigma X, and it flips the gate. So when you talk about a X gate, it flips. So if you apply a this matrix to any of the what you call the states, the state is flipped. So that means if you have a 0, if you multiply 0 by this matrix, kit 0 is nothing but 0 1 column. So if you multiply 0 1 by 0 1 1 0, you have 2 by 1 into 2 by 2, you will end up in a actual value of kit 1, which is nothing but 1 0. So you can do XYZ operation, as we said. Pi radian is 180 degree. So the rotation depends on the y-axis, x-axis. So if you rotate around x, that is one. If you rotate around y, that is different. If you rotate around z, that is different. So these are all the XYZ of this. And you can see, if you multiply by the same matrix, that is x by x, y by y, z by z, all of them will turn into an identity matrix. That's a standard. And example of NOT is, so when you do a NOT operation, X operation, it moves the X, moves around the X axis. So if this is the X axis, the Y and Z plane, so this is the Y and this is the Z. So this YZ plane rotates around X by pi by 2 radians. So that is the interpretation here for the block sphere. I'll move on, we'll understand. This is a bit of a geometrical thing, so difficult to comprehend, but we have seen it in the quiz kit as demonstrated by Professor Gokhale previously. So I'll just, important gates we need to know is the swap gate, C0 gate. Why swap gate? Swap gate is just you short circuit the two, the qubits, and what it will mean is this will go this way, this will go this way, so they will flip. So swap. So basically you're swapping. So example of a swap operation, it's not flip, it is X is flip, this is swap. Swap means, so before we go into that, let me just talk about Hadamard gate. This is the most important gate of all the gates because it does the superposition, enables superposition. So if you have kit 0 and kit 1, and when you apply a Hadamard gate, Hadamard is nothing but your, we have seen the Hadamard, not here, okay. So there is a matrix for Hadamard which is here, sorry. So if you have 1, 1, 1 minus, if you apply, of course 1 by root 2 is for normalization. If you apply a Hadamard gate, then you will get the superposition. So if you have kit 0 and you're applying a Hadamard, then you will get a superposition of 1 by root 2 of kit 0 and kit 1, and that will become plus 1. So basically you can see X is the plus and minus representation. Kit plus and kit minus are here. So when you have a kit 0, which is here, if you apply the Hadamard, it will make it in this direction. So this is 0, kit 0 will become ket plus. So this will move from here to here, whereas ket 1 will move from here to here to here, which is minus. So what it means is it's a rotation. So the rotation applied to ket 0 and ket 1 causes it to become plus and minus. So if you have this ket 0, ket 1 superposition, it will change to this x direction. So we call that when you apply a block sphere, when you apply a Hadamard to a particular Hadamard operation, which is a matrix operation, to a spin up and spin down superposition, it will get into. So when you say superposition, what it means, ket 0 and ket 1 are together. And that is the superposition of. So psi equal to ket psi equal to alpha ket 0 plus beta ket 1. If you apply a Hadamard to it, then it will the 0 will flip towards this and 1 will flip towards this. So z axis, whatever we had the superposition, will go into x axis. So by applying Hadamard, we are transforming a what you call the qubit from a standard basis to Hadamard basis, which is x direction. And you can measure it. Once you measure, it will collapse. Then it will be a different story. But important thing is Hadamard gate. The definition of Hadamard gate, which is different from poly XYZ, in the sense that here 1 1 1 minus are the these are the eigen values and the vectors associated with them. So what I will do is now, so Hadamard of Hadamard is always 1. So that means if you have x basis, if you have standard basis representation ket 0, ket 1, if you apply Hadamard, it will go xy, that is plus x axis, which is plus minus. And if you reapply Hadamard, it will come back to the. So we can always switch the what you call the basis in which we measure from z to x and x to z by Hadamard. That is the important of this is the most important game, because all the application of quantum require superposition for getting high performance or multiple parallel operation. The other operation is swap and the C naught. C naught is nothing equivalent of exclusive OR with a control knot. So this is the controlling dot and this is the knot. So knot is also represented as plus or XOR. So controlled XOR or control knot is what? Control knot is equivalent to XOR. And XOR does what? Remember that 0, 1, 1, 0 will become 1. Anything 0, 0 or 1, 1 which is same will be 0. So 0 does not affect. If this is 0, this will not get impacted. But this is 1, then this will flip. So that is the flipping that is happening. You can see. And here you can see the 2 by 2, because this is qubit 1, qubit 2. So this is 2 qubits. So this is 4 by 4 matrix. Normally all identity will be 1. But whenever there is a 1, this flip will occur. So if this is 1, which is nothing but LS bit, and this is MS bit. So if LS bit is controlling, and if the LS bit happens to be a 0, then it will flip this to 1. And if LS bit is so this is the combination which represents, because this is 1 0 0 0 0 1 0 0 0 0 0 1 0 1 1 0. So you can see that if this is a 4 states, this is the state, this is the up, down, down, down. So this 1 0 and 0 0 are the 2 qubits. When you apply, so this is 0, then it should flip. And the same way, if this is 0, no, the other one is here. So these two are the bottom. This is, so we have got LS bit and MS bit. And since we are showing, you can show it MS bit. So these are the 2 zeros. Here the whatever ones will be flipping. So that is why you have flip here. Normally this would be identity matrix 1 1. So 1 flips here and 1 flips here. So that is the C naught with a C with a naught, which is exclusive. So what I would say is, for essentially it means this is described as if you have A and B as 2 bits, qubits, and if your AB is the tensor product, then it will become A and A or exclusive or B. So that means if A is 1, if this is A is 1, then you will flip. and that's what this is representing. This is for the, and swap gate is nothing but if you have AB, it will become BA. So swap and C0 are very important, and we have also looked at the all the gates now, fundamental, and we have also shown the how the what you call block sphere operation happens. So with that, I'll move on to the next one, and this is Toffoli gate. And Toffoli gates. So first, before even talking about any gate, this is a how many? 1, 2, 3, 8. So this is a 3-qubit gate. So C0 we saw, C0. So control of naught, that is the 3-qubit, which is a Toffoli gate. And Toffoli gate is described by the inputs as 0, 0 up to 1, 1, 1. So the in Toffoli, control of control. That means if the control bit is 1 and control of another control is 1, then it flips. So 1, 1, 0 flips to 1, 1, 1. Control of control 1, 1. Therefore, the last one flips. So only the 1, 1, 1 and 1, 1, 0 flip. You can draw any flowchart. Same way we could have drawn what you call for these also, and then describe the truth table. So we can use truth table input output to define the gate, and then accordingly we can place the matrix. So this is what Toffoli is a universal gate. Important to note, because using this gate we can create a knot, CC0, which is here xy comma x and x or y, and this is CC0 of using for getting the knot. We do this one 1, 1 knot of x. So this is nothing but these are Toffoli gates being used to create AND, NOT, or NAND, because CC0 can be applied with following inputs and be able to get the classical gates. Toffoli gate is called a universal gate, not unitary. Okay, it is universal gate. Unitary gates are one which are unit, and whereas Toffoli gate is one of the gates which can be used. So all classical implementation can be used with Toffoli alone. And so, but that is why a lot of standardization, when semiconductor people, they prefer to use one gate, and that can be replicated a number of times to do any of the gates. So therefore Toffoli gate is popular in that. And the rest of the gates which are rotating within that, they are called Clifford gates, Clifford of qubit 1, 2, 3. So Clifford and Toffoli, if we combine Clifford dash T, which becomes the universal combination of all gates can be implemented. Now I will come to discrete Fourier transform. Gokhale sir, are you available? Can you take this? Gokhale? I can. Okay. Are you able to take this? Can you start with the DFT? Start speaking. Gokhale?
Prakash, I am not able to, I do not know, my audio is able to reach you?
Okay, okay. Yeah, audio is able to reach. We can hear you. And I have put the discrete Fourier transform, whatever the graph, time to frequency. Yeah, if you can see, fine. If you can't, then I will talk. Let me know. Are you able to see the slides?
Prakash, I'm having an issue here.
Okay, okay, no problem. So let me continue. You interrupt me whenever you have anything you find which is you want to say. Okay. So let me continue. So what we have here is a discrete Fourier transform. So algorithms are important for implementation of quantum, and in this
Hello.
with respect, yeah,
Hello.
yeah, go ahead. Yeah, you want to say something, Gokhale? Looks like we have audio issues. Gokhale, is it audio issue or shall I continue? Do you want me to continue? Okay, so I'll continue anyway. If he jumps in, let him. So what we have is a time axis. So normally every quantum operation in with respect to time is a transformation. So if we take samples on time basis, T0, T1, n samples we take of any signal, In Fourier's term, we do a time to frequency domain transform. So whatever is in time domain, a corresponding frequency will be so frequency term will be generated. So if you have T0, you'll have corresponding F0, T1. So this is a transform, right? Time to frequency domain transform. Now that is in terms of, if it is a analog, then you will get a continuous. But in case of discrete, you are going to get only samples, and the samples will have some. So this is a DC amplitude, means it's a constant. If you take a constant, you are going to get different frequency F0 to Fn minus 1, and that is what is represented. And that is called as discrete Fourier transform. So transformation from time to frequency domain in signal processing is done in continuous, whereas in our case, we talk about discretely done, discrete Fourier transform. So you transform. Now the same transformation principle which you do for time to frequency can also be applied for quantum. And that means whatever is DFT, discrete Fourier transform, can be applied to quantum. So if you have X as a sample, which is represented by a what do you call a column matrix, X0 to Xn minus 1, the transformed value Y equal to function of X, which is X, is nothing but represented by Y0, Y1, Yn minus 1. So the Y is the transformation brought to X based on the number of samples here. Okay, we are talking right now samples in digital terms. Now this can also be represented by Y equal to, because you have to normalize, and the normalization can be done based on if you have n samples, then you divide by 1 by root n. And so sigma j equal to 0 to n minus 1, where we are representing Y here, Yk we are representing. So Yk is nothing but j equal to 0 to n minus 1 of whatever xj, which is the input, multiplied by a rotational vector, which we call as omega minus kj. We'll describe this, which is nothing. Omega is nothing but 2 pi. 2 pi is nothing. Pi radian is 80 degree. 2 pi is 360 degree. So 360 divided by the number of n. And if it is 12, then it will be 30 degree. So this term omega minus kj, where j increases from 0 to n minus 1, will be rotating by 30 degree if n is equal to 12. So this is the representation, and we can look at this representation here, like I have shown here, omega 0, omega 130 degree, omega. So this is 12. So if n is equal to 12, 360 degree, 2 pi radian. Pi radian is 180, 2 pi is 360, 360 divided by 12. So omega is nothing but e to the power I 2 pi by n. This is because you have got an imaginary axis and real axis. So if we said psi equal to ket alpha ket 0 plus beta ket 1, alpha beta being the real imaginary number. So imaginary number will have real component and imaginary component, and the angle that it makes in that real imaginary axis is the angle theta, and therefore e raised to I theta, or e raised to I 2 pi by n we call it, and that is also equivalent to we can say, if there is a vector C which is made of component A and B, real and imaginary, then A plus IB equal to C is represented by C equal to, which is the square of A square plus B square is C, that Pythagoras, as you know, and that C is equal to C into e raised to I theta, where theta is the angle. So which is equivalent to cos theta plus I sin theta. So basically sine and cos components are used, and that can be represented either in trigonometric sense or in the angular quantum sense. But this C for quantum has to lie here. So therefore, you have to normalize it by dividing C by A square plus B square. So that becomes unity. So basically, we want to operate only on the unit circle. It said here it is shown in 2 dimension vector, because you have got imaginary axis. Cartesian coordinate is different. There is only real xy, but this is not Cartesian. This is imaginary real. So therefore, there is a difference, but only to make sure that you understand when we talk about the Fourier transform from discrete Fourier transform from output y being obtained by input x by multiplying with the angular, which is the rotation. And so in quantum, everything is a rotation. You keep on rotating, you can rotate clockwise, anti-clockwise, and if you rotate one way or the other, it changes. So the basic principle of discrete Fourier transform, it adds up or it destroys. So either it is called constructive interference or destructive interference. Because of that, if it is constructive, then you get one for each one of them, because at the end of it's a quantum discrete QFT, not DFT. DFT you may have different magnitude, but in quantum we always have probability of being unity. We always get one. So if you have 0 to n minus 1, add 1, then you get n. So by constructive you can get n. By destructive, that is if q equal to 0, mq, example omega mq, m is the angle. You can see that m we represented, m is 0, 1 to n minus 1. For 1 to 11 example, 0 to 11 for example, for 12. So that m and the q is the component, either it is 0 or 1. If it is constructive, then this will be 0. So omega raised to m, each of them being unity, you get n. If q is equal to 1, then what happens? Then they will go into destructive, and then you will get so if q is equal to 0, we get constructive. If q equal to 1, we get destructive. Because if you look at this one, if everybody is pointing, this fellow will cancel this fellow will cancel. So each one of them cancel each other. What do you get? It is 0. So that's what it happens in destructive. So you got constructive and destructive, both are possible, and you can do axis rotation, or you can do this. So in quantum, either you can rotate the vector or you can rotate the framework opposite direction. They mean the same thing, but the angle how they represent is, one of them is, if you represent so pictorially, if you see, you get a omega minus m or 1. So either I can go omega 0, 1 to 11, or I can go omega 0, omega minus 1 to omega minus 11. So you can do that is the counterclockwise or clockwise. So accordingly, you will get a measurement. If you do counterclockwise, counterclockwise means, the clockwise was this, counterclockwise. So in counterclockwise, we get a negative. In clockwise, we get a positive. That is the notation here. This is for notational purpose. And so this is about the nth root of unity we spoke about, and discrete Fourier transform, how they are connected. This is for the purpose of describing the QFT algorithm. QFT algorithm, so basically what happens is, as Professor Gokhale put it last time, if you have 1, 1, 1, 1, 1, 1, this is omega raised to 0 is always 1. Anything raised to 0 is 1. So therefore, anything in the zeros will always be 1. Or in terms of Fourier, you call it as what do you call, the first is all DC components, second is always the first harmonic, second harmonic, third harmonic, nth harmonic, n minus 1 harmonic. So if you have first harmonic, you have omega minus 1, minus 2, omega m minus n minus 2 in the matrix. This is a matrix representation of what we did here in the whatever here, the summation matrix. So whatever we described in summation terms here, this is being described in matrix there. Because if you have n minus 0 to n minus 1, so it will be n by n matrix. So that is what the representation. If you have 0 to n minus 1, which is n by n matrix, so this is n by n matrix. First of these is the what do you call, the DC. Second is the first harmonic. Second harmonic will be minus 2, minus 4, minus 2 n minus 1, and the last one will be minus n minus 1 to minus n minus 1 minus n. So for n equal to 2, if we substitute in this, we get this matrix, which is 1, 1, omega raised to minus 1, which is in this case minus 1. So you can see that the same thing is applied here, and ultimately we can take this matrix, and this is equivalent to 1 by root 2, 1 minus 1. And if you remember, recollect, we go back, we had seen that Hadamard is 1 by root 2, 1 minus 1. So basically, coming down to, if I have to implement a QFT algorithm for 1 qubit, it is nothing but I apply a Hadamard gate. So that's what it means. So 1 Hadamard gate, 2 Hadamard gate, 3 Hadamard gate, that is what it will end up in. If we have q equal to 4, then we will have the same matrix which we had done here, 1 1 1 1 1 omega minus 1. So this will be the matrix. So that is 1 1 1 1 omega minus 1 omega minus. So this is what is represented here. This is for this is for n equal to 4, 2 qubit. So this is the matrix which we have, right? Which is the one which is 2 by 2, 4 matrix. So we have to take 4 terms out of this, 1 1 1, one more of this, and 4 terms. So those 4 terms are coming out as this. And if you apply this, which is 0 1 2 3, if you have I raised to k minus 0, that is 1, I raised to minus 1, that will be I square, which is minus 1, I raised to minus 2, which is 3 times, so it will become minus 1, because I square is 1, and so this, and similarly I raised to minus 3, that will become I. So basically, if you look at this, you may not have noted, now you note, this is 1 I minus 1 minus I, and the same thing is reflected here in our terminology here, this 1 minus 1 minus I 1. So for a because you divide by 4, then you get those 4 quadrants, and that 4 quadrants angle values are this, and this is the calculation. I'll leave the calculation apart because that can be done anytime. We have to accept that this is the matrix omega, which is applied for QFT. Why do we need QFT? Because we, for Shor's algorithm, we'll need QFT. So I'm going about the inverse QFT. Inverse QFT is nothing but so this is described as UQFT, that is unitary gate for quantum Fourier transform. So all our gates in quantum are represented as U of something. So you can call it U of anything. Like example, we had done a standard logic you have seen previously, U1, U2, U3, U4. So generally the gates are represented as unitary gates, and that is what we show in our QFT, and that is the universal gate. And so for a IQFT, we are talking about if I have UIQFT. So UIQFT into UQFT is equal to UQFT into UIQFT. Basically minuses and plus, if you have 2 of them, and if you multiply, not the multiply, they do a obviously a what do you call, the tensor operation, which is nothing but every term of one matrix being multiplied to every other term, and then total, it will come out to identity matrix. Basically all ones will be there, n by 1, all diagonal of all other than the diagonal ones will be 0, and that is identity. So what it means is it is reversible. So whatever your UQFT, you can apply a UQFT, they are inverse of each other, and the term totally will come out to 1, which is nothing but null in this case, which is a identity matrix. Everything in quantum, either you use a null operator or null gate, which is I, or a U gate. So I gate, U gate, U of many types, UIQFT, U C naught, U whatever, U CC naught, U Toffoli, U whatever. So you represent that as U of that, and the corresponding matrix which is operated on. So example, U swap A B, you get a BA. We have seen that. Again, this is just an explanation, just to say if you have similarly, we talk about U swap Q gate, which is IJ, then they are multiplying and coming to the same conclusion. And I will leave that because after all, a U swap, let's say 5. So we want to have a 5 qubit, and the input is 1 0 0 1 0 1 0 0. Then swap operation will be nothing. What we should see, swap means what? A becomes so we swap AB. First thing is, if you look at the swap of AB, it will clearly show that if you do a swap operation, you are doing nothing but connecting the qubits, and thereby you are flipping ket AB. If you have, you get ket BA. So if I have ket ABCD, what is it going to happen? So it is going to be DCBA, right? That's what we expect. And so that is what we are trying to do here for a 5 qubit operation swap. And you can see here U swap, since we have 5 bits, if we have this, then the reverse should come out. So 00101 DCBA or ECDBA, A, B, C, D, E, E, D, C, B, A. So 00101. So 00101. So it is swapping. So that is the swap operation. And you can do this by one by one. And you can use swap 1 with 3, 0 with 4. So this is odd number. So if it is odd, the middle one will remain as is. Only this 1, 2, and 3, 4. 1, 3, 1 will swap with 3, 0 will swap with 4, and the middle one will remain. And that is what is happening. So this is the swap operation. This is why is this described is because we want to show on the circuit. If you have a quantum circuit with 1 0 1 0 0 and you are just swapping, then you got to swap this with this, this with this, this with this, and the middle one remains as is. And that is how it comes out in inverse. And the same thing can be reduced. Instead of doing 5, you can just do it 2 swaps. So you don't need a 5 space. This is showing 5 swaps. You can do the same thing with 3 swaps. So that is called optimization. So you can optimize with 2 swaps rather than 5 swaps, and that is the crux of optimization, to give you some idea. And here is a circuit implementation for the swap. So what Professor Gokhale has done is he had presented this previously, and just wanted to make sure that it can be used using IBM QuizKit. So you can define your swaps, 2 swaps for the 5-bit. We said 5 swaps can be optimized to 2 swaps. So we do 2 swaps, and here we have represented, because initially if you have 5 qubits, 43210 ms bit to ls bit, and if you say fifth one is a 1, fourth one, that is fifth is nothing but 4, q4 fifth, and the third, which is 4 and 2 are 1, because we are starting with 0. And then so we swap the extreme, we swap the in between, and middle one we leave and do the measurement. These are measurement symbol. If you do, then you get this. And you can see in simulation we'll get a perfect because there is no interference. But if in real computer you do, you may have some noise in the various levels, because we have got 2 to the power 1, 2, 3, 4, 2 to the power 5. So that means 2, 4, 8, 16, 32. There are 32 numbers, and out of the 32, only one of them is, it collapses to one of them. So we get the swap based on this, and that is to show on real computer how it will come. So this is not at the end of it. This is at somewhere in the midpoint, I believe. And so that is why the simulation is not showing 2 ones, which we expect probability. But no, it is 2 ones, but it is on 0 0 1 0 1. So this is correct. This is the final result, because 1 0 0 1 0 1 is the result, whereas the input was 1 0 1 0 0, and the output is 0 0 1 0 1, which is swapped. So this is the swap circuit, and hopefully this explains what the swap implementation of 5 qubit using the 2 swaps for quantum Fourier transform. So I had shared with you, because everybody cannot use QuizKit, we had last time shared something called Quark. Quark is a open source tool. You can go over the web and implement directly. So if you have any exercise which you can do on QuizKit, can also be done without having any resource. So this algacert.com Quark is what we recommend. If you give any exercises, we want you to try it out there over the web with no additional compute capability from your side. As long as you have a web, you can go click on it. Of course, there is some idiosyncrasies in this as how you can use that, and there is a tutorial on that. You can go through the tutorial and then implement the gates which we want you to know. So with that, I will jump to Stokes algorithm, the last algorithm. And what we have is a product of 2 primes. So if I have a number, let's say example, let's say here we have example. Let 2 be, let 15, which is equal to 3 into 5. 3 is the first prime number, 5 is the second prime number. So if you are given a number 5, you should be able to factorize and get the 3 into 5. But this is easy, even though it is easy just to go over. Suppose we have n and we just don't know what we can start 2, 4, 8, 1. So if you try to do a repetitive of a factorization of number, like example 2, 4, 8. So if you do another multiply by 2, it will go to 16. So it is already becoming, so if you take a modulus, if you have 4, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8. So if you take a modulo approach of whatever your a raised to k, so if n is equal to 15, which is equal to 2 to the power 2, 4, 8, 16, 2 to the power 4. So 15 mod n, if you do, you will get 2481, 2481. It will keep on. So where repetition is 4. So what it means is, if 4 divides, which is because modulo of anything greater than n is 15. So 15 can be accommodated within 16. So 2 to the power 4. So the modulo is 4. That means what? The repeat factor is 4. So if you get a repeat factor, if you can identify from a given number, now if I give you a billion, then it is hard. But if it is this 15, you can easily get the greatest common factor, and therefore you are able to get. And by taking the repeat factor, how repeat, when we take a raised to k, so any number, if I give 100, so what is the next number, which is 2 to the power? So 124, 64, 128. So 2 to the power 7 will be 128. So the repeat factor for determining anything in the range less than 128, a prime number, will be that number. So that the repeat factor is in that case 7. So we'll have mod as 7. So once you get that number, all you have to do is you have to take a greatest common factor and divide. So 4 divides 4 means we need 4. So what we have done is 3 minus 1, 5 minus 1. So this is equal to 4 divides 3 minus 1 and 5 minus 1. So 3 into 5. So you take whatever prime factor which you are going to get p number, p minus 1 into q. So p into q is your number, let's say. So p minus 1 into q minus 1 gives you 8, which is divided by 4. So the repeat factor is 2r factor in this case. So once we know the period r, it's not too hard to find the n primes p and q. But unfortunately, finding the exact it takes extremely long time in classical computer. So if I give you a factor of, like calculation of pi, similarly this factoring is a very important thing. It is very complex. This is, if I give you a number which is prime factor of this billion, you first of all don't know whether it's a prime, whether it has a what prime numbers are there. So the determination of algorithm is based on some flow chart. This is the logic behind it. So I'll share with you before I share the logic, all I am saying is we need to use inverse Fourier transform to find the period. So here we found the period by just guessing something, right? And because we were able to do it from having the starting point as a raised to k, which is greater than 1 by this, and then say, oh, the repeat factor is 4. But which is, so the repeat factor is 4, and then that is what we were able to get it. But this is not easy for a billion number. So what do? We make sure that we use the Fourier transform and then apply the Shor's. So the Shor's algorithm is nothing but applying of QFT to determine the R, because we know angular, right? So if you have n equal to 16, like n equal to 12, we found that there are 30 degrees. And then we could get that formula using the matrix. Same matrix and same circuit implementation, we can get QFT. So Shor's algorithm, what it does is, it factors a large number. So you try some number, choose a number, random number, which is a less than n, and then see whether this GCD is equal to 1. If GCD is greatest common denominator, or you can call HCF, highest common factor, whichever. So once you get mathematically, classically, we can implement, and if it is 1, that means no, A and N are already we got the prime factor. If you choose number and randomly, and if it is not a GCF, then if it comes out to be 1, then we have already there. If not, then we have to apply the repeat factor determination. Once you get repeat factor, the repeat factor, is it odd or even? Based on odd or even, we apply. If it is odd, yes, then again choose another factor. Because why that odd number even factor is because you need to have a number. If it is odd, then how will you get the multiplication? So there are some logic in that. I leave that. At the same time, we have to, once we have got the repeat factor, and if it is even, then we are a raised to, because even means we are able to do a mod, because 0 mod we want to the end. So 0 mod n we calculate, and that is how we will be able to get. So this Shor's algorithm is a bit complex, but for a class of learning, we just wanted to say that it's a bunch of algorithms are used for a bunch of other algorithms. Like we had done the Deutsch constant and balance, which Professor Gokhale had explained to you last time. And then we had what you call the search algorithm. And then now we have Shor's algorithm. We can only touch the surface of it. We really can't do detail, but having to understand that there are many algorithms, they all depend on each other. One exploits the other, and the periodicity in this case for the QFT is used by the Shor's for determining the prime factor. You can go through this detail, but I will leave you with some exercises in the class to figure out what is, are they superpositioned, are they superposition on Hadamard basis, that is X basis, are the standard Z basis, are they entangled, and how do you prove the clone theorem? So these are some of the exercises I leave with to you, and that should bring us to the end of the course. The conclusion: gate circuit and quantum algorithms are key to digital quantum. Now I am saying digital quantum because this is discrete. Quanta means quantity, and how much that is measured. This is subatomic particle base. So the quanta is very low, like photon, like characteristics of electron, photon being massless, whereas electron being some mass, and the properties of them, like your positioning, like if it is 1 qubit, if it is a helium, then it is 1. If it is so, what is the state of it? Whether it is in ground state, excited state, how we use that for the digital computation using the quantum. That is why the gate circuit I explained, and algorithms. These are the two key aspects from application, because we are talking about learning quantum for application. And for application, we don't need to know physically anything. Logical qubit is enough for us, although physical qubit may be required for what you call stabilization and for fault tolerance and all, but that's not the territory. We are focused on the application, learning application, and for application, we need to know the circuit and the algorithm and how the algorithms are applied, so that the digital quantum, which is nothing, discrete quantum, can be applied using the transpilation, compilation, etc., to convert into corresponding analog pulses, which is controlled by the control circuit. We have seen the stack previously, so you understand. But we did cover only for digital, in the sense we only covered for the computing, quantum computing based on electronics, and not based on the adiabatic, which is based on the heat transfer and thermodynamics, where you maintain a particular what you call state, adiabatic state. That means neither the heat is transferred nor so heat is maintained constant. We call it as entropy. So that is based on that, and I think that is what it is. And the basic vector, we have ket factor, we saw the ket0, ket1, we also saw the matrix operations, and then all operations in quantum or tensor operations. You have to remember that. And the other factor is we also need to make sure that we can use at least one SDK for quantum coding if you are going to do any coding exercise. QuizKit was represented. There are many like Penny Lane. They are available on the what do you call the Amazon's or Google's Azure Quantum. So not Google, the Microsoft Azure Quantum or Google Circ. So those are the libraries and SDKs available which you can use with Python. That's the best for the programming. Since it is more data centric these days with the AI/ML, so QML, quantum machine learning, is what is becoming more popular. So you can choose what you want to learn and the application area. So we have introduced all the aspects that we can bring into the table. I'm 7 past 11, 7 minutes overshoot, but that was, we started late 9 minutes. So we are completing with this the course here. I will open the floor for questions. So if you have any questions, please ask at this time. Thank you. Gokhale, anything you want to add? Are you there, Gokhale? Yeah. I hope I had admitted everybody. Yeah. Anybody, any questions? So let me start with Jane. Anything you want to ask? Matthew? Suresh?
No, thank you, Prakash. I'm just absorbing it all. I mean, yeah, I'm just absorbing it all. It's gonna take me a minute to catch up, but I honestly, I love it. When you were talking today, it just felt good. So thank you.
Oh, thanks, Jane, for that, and I appreciate the. We always are happy if somebody appreciates and learns from this. Our goal has been voluntary, and Professor Gokhale, along with Quantum, he's from the Emerging Open Tech Foundation, EOTF, based in Mumbai, and along with the Quantum, what you call Silicon Valley Quantum Group, Quantum Computing Group, which is focused now on QML. We had advanced presentations, and Dr. Taposh is the Taposh is the leading it, and I am helping along. And so we look forward to your being able to take it. I will put all the recorded message. We are still to put all of them, and because Taposh was not able to uh, come today, I'll work with him to get all the recordings together. And if we have any corrections, we will also apply corrections. But most of the time, I think today's lesson has been completing all that we did previously to ensure that everybody is on the same page. And I will also send exercises to all of you. We have more than 718 members, out of which I think 30 to 40 have been active, whether they view the record or view the online. And online is always better because that gives you better understanding. Yeah, Suresh, thank you for your kind words. We look forward to making sure that all these are posted out for everybody to use and learn. And we have definitely plans for to just inform you, we have formed a quantum information technology QIT working group under IEEE, which I am chairing, and we have Gokhale, Chintan, then we have members from various universities in local. All of them are there, and look forward to working with you all. So at this time, Gokhale, thank you for your message, and I appreciate for your participation at a short notice. And hopefully we'll be able to provide this record to everyone. I will stop the recording here. Hopefully we are able to stop the recording here. Stop recording. Okay.